Okay. All right, so increasing, decreasing, constant. We're taking a look at a graph, and we're trying to decide where this graph is going up or down, or flat. One of those two. Increasing, decreasing, or constant. Now, when we do that, x is always moving from left to right. So as I'm going from in this direction, okay, just like you read a book. Okay, so we're reading a book going left to right, and this is going uphill or downhill. That's all you're looking for. Okay, so as I start here on the left, I start here on the left. The graph, as I go left to right, the graph is going down. Right. So this part right here would be a decreasing section. Just put a little d there. Okay. Once I hit this point right here, it switches over, and this spot's flat, so that's a constant section. Okay, so I'm not going up or down. Okay, as I hit this point left to right, it starts going back up, so this is the increasing section. I hit this point, changes back to constant, back downhill, this goes to decreasing, increasing, decreasing. Pretty easy, right? Now how they wrote that is always kind of weird as far as the notation, because they used interval notation, which looks kind of like an ordered pair, which is kind of silly. Okay, so let's say I went this graph right here, and we'll say this is 1, and then 2, and then 3, and then 4, and then 5, and then 6. Pretend those are even increments. Okay, so how you would write that, if you were to write this decreasing section, okay, assume that this one would go forever if you want, or if it looks like it stops, depending if they throw an arrow on there. If this was going forever, it's going as far left, which is negative infinity, so this interval right here will go from negative infinity all the way to 1. So it would go from negative infinity to 1, which kind of looks like an ordered pair, unfortunately. Okay, this interval right here is where it's constant. The left endpoint is 1, the right endpoint is 2, so this interval is constant from 1 to 2. We increase from 2 to 3, so this would be 2 to 3. These are not ordered pairs. That's what kind of sucks about this notation, is they look like ordered pairs. But we just say that they're intervals, and then everybody's happy. And then likewise 3 to 4, and you guys can probably fill the rest of those out. Right? Make sense? It's not too bad, I hope. Now what we want to do is we want to take a look, as we look at this, we look at this graph right here, we want to think about what we've been doing with the derivative, right? Now the derivative does for us, it finds the slope for us, which is kind of nice. That means that if I pick any point in this region right here, this is a decreasing section, right? If I look at the derivative of that function, what should all the values of the derivative be in this little zone right here? Negative, it's going downhill, right? All the slopes here are negative, right? What are all the slopes in this little region here? 0, and then here's positive, 0, negative, positive. You're right, you get the idea, right? Okay, so the first derivative is going to tell us if it's increasing or decreasing or constant. Okay, now it's only going to switch at those critical values, at those critical points. That's when we're going to switch from increasing to decreasing. So what we're going to do is we're going to find those critical points, kind of like our graphs that we've done before, and we're going to try to set up little zones for us to find out where the heck this graph is increasing or decreasing. Okay, so let's go ahead and start with the function like so. X to the third minus 3 halves x squared. And I'm going to go on the open interval for this one. Okay, so we're going to go on the interval. It's going to go from negative infinity to infinity. So that's going to include everything. Sometimes they might close off a little interval for you and say go from 1 to 5 and then figure out stuff in between there. But for now, we're just going to assume it's all numbers. We can go anything that we want. Okay. So what we want to do is we want to find those critical points, those critical values, and then find out where it's increasing and decreasing right around that. Okay, it's only going to switch at those critical values. So if we find the derivative of this guy, which is pretty simple on this one, we got a 3x squared and then minus, what, 3x? Okay, so as I find the derivative, let's go ahead and find our critical points, which we found before. Critical points are anywhere where this is 0 or undefined, right? There's no spot where this is undefined. This is going to be continuous all the way through. So all we have to do is set this one equal to 0, and that'll give us all of our critical points. Okay, so we're going to go ahead and factor that. We take a little 3x out. You get x minus 1. And so then 0 and then 1 are your critical numbers. Okay, so these are our critical numbers. Okay, now what that means for the graph, is that all the way to negative infinity, once I hit 0 right here, any number in here, it's going to be the same. It's going to be either increasing, decreasing, or constant. It can't change over here from 0 to 1. Or I'm sorry, from negative infinity to 0. Okay? From 0 to 1, it switches. So from here to here on this little interval, it might be increasing or decreasing. We don't know yet. And then once we hit 1, from 1 all the way to infinity, it's going to be the same, increasing or decreasing, whichever one it happens to be. Okay? So what we would do is we want to find out the intervals for which this is increasing and decreasing. Okay? So first thing I'm going to do is find out what this little interval is right here. Okay? So I want to find out if this is increasing or decreasing on this side of the axis. from 0 to 1? Well, let's just plug in a number, 3x squared minus 3x. Let's plug in a number that's in this interval right here and see if my slope is positive or negative. Okay, so I'm going to plug in my little interval. I'm going to go from negative infinity to 0. Okay, so that's my little interval that I want. I want to know what the derivative is as some number inside of that interval. Okay, and the nice part is you can pick whichever number that you want. Okay, so pick a number between negative infinity and 0. Negative 5, sure. Negative 5.
495,000.
Negative 495,000. Feel free. It doesn't matter the value you pick. Okay, it doesn't matter at all because in this region it's always either going to be increasing, decreasing, or constant. It's always going to be one of those, and it's going to stay that way. Okay. So in this little region, we pick negative 5 on this one. So plug negative 5 into your derivative right here, and tell me what you get. So negative 5, 25, I got a positive number. You guys get that? I don't care about the value, right? I care that it's positive. That tells me that this little part in here is increasing. Okay, so I have an increasing slope. All of the stuff is in here is increasing. Okay, so that means it's probably going to go something like this. And who knows exactly where it goes? But I'm going to be increasing all the way through this zone right here. They only switch at critical points. It's the only time they switch. Okay. Now I want to check my second interval, which is this little interval right here, in between the critical points, basically, 0 and 1. So I'm going to check 0 and 1. And so I want to find some slope at a value between 0 and 1. Now you get to pick whichever value you want, right? So pick a number between 0 and 1. Half. Okay, so let's pick a half. So let's find the slope at a half. Okay, so plug in a half right there, and then see what you get. All I care about is positive or negative. I don't care about the value. All I care is if it's the sign. If it's negative, okay, so that means from here to here, in this little zone right here, it's decreasing. Okay, so in that little interval from 0 to 1, it's got to be decreasing. So my graph's going to be going down somewhere in there. Okay, decreasing somewhere in there. Okay, now I hit this other one, this 1 to all the way to infinity, right? So I've got another little zone right here, and it could potentially just keep going down, or it could flip back up and go up. We're not really sure. Okay, so we're going to pick, once again, another interval here. We're going to go from 1 all the way out to infinity, and we want to pick some value between 1 and infinity to plug into our derivative. And I can pick whichever point I want. 2 is a good one. Sure, why not? I'd have picked 8 million, but 2 also is fine. Okay. So plug in a 2 and you get a positive, okay? Don't care what the number is. I care if it's positive or negative right now, okay? So I know that this right here is going to be back to increasing. So the zone over there is increasing, so I know my graph is going to go like this. And I know it's going to continue increasing forever, okay? It has to. There's no other critical points out here, so there's no other place for that to happen, okay? So we just kind of ballparked it there, right? Let's go ahead and graph it just to see if I'm... Let's see, x to the third minus 3 divided by 2x squared. And let's go ahead and just zoom 6 it, see what it looks like. Okay, it looks pretty good. I might zoom in just a little bit here. Okay, so does that agree with what we did? Now, my graph might not look exactly the same. I don't care, right? It doesn't matter what my graph really looks like. What matters is my zones for which I'm increasing and decreasing. My intervals would still be the same. I would still say from negative infinity to 0, I'm increasing. Whether I have that graph or whether I have this graph, it doesn't matter. Okay, those graphs would be essentially the same as far as increasing and decreasing. Okay, I'm decreasing on this little zone, so from 0 to 1, I should put brackets, sorry. From 0 to 1, I'm decreasing, and then from 1 to infinity, I'm back to increasing again. Okay? That makes sense, I hope? Now, they're only going to happen at critical values. There's the only time that it's going to switch for us. Yeah?
I don't get why if you plug in negative 5 to the f prime, why if it's positive is increasing? If it was
because what is f prime telling me? That's slope, right? Because the derivative is slope, right? So I know that I picked a point right here, and I know that the derivative was positive, or the slope was positive, which means it's increasing, right? It's going uphill, right? So somewhere on there it's got to be increasing. Now I could have picked, like I said, whatever point I want in that range, I could have picked this point, slope is still increasing, okay? So any point on there is going to work. It's not going to be a huge deal, okay? All right, cool. We feeling semi-okay about that?
Yeah.
Not too bad? We can do a couple of those, but I think you guys are okay, right? Okay, they only happen at critical values, critical points. We don't need to spend too much time on the increase and decrease. The big thing for today is the first derivative.
We're all constant. So we're
constant is where the slope would equal 0. So if you were to plug in, let's say you had an interval like here. I should probably put it here. If you had an interval and this ended up being 0, then you know it's going to be a constant. So, yep. Usually the constants happen like on the piecewise functions, which are weird anyway. So constants don't happen, to be honest. So, all right, first derivative test. Let's take a look at this. Okay, now, kind of along the lines with the Rolle's theorem and the mean value theorem, it has the same stipulation. So if I'm talking about some kind of interval, which we've been doing, like negative infinity to 0, right, it's got to have two things going for it. It's got to be continuous and differentiable. Okay, so that stuff still has to hold for all of our tests to work. Okay, so let's do the first derivative test. It sounds hard, right? It's not. It's so nice. First derivative test says this. Let's say I've got a graph, something like this, kind of like the one I just did. Okay, so there's my graph. Similar to the one that I have up there. Okay, what I want to do is I want to find actually maximums and minimums, relative maximums and relative minimums, based on this increasing, decreasing idea. Okay? So what I'm going to look for is I'm going to look for those zones that I just looked for. This right here would be increasing. This right here would be decreasing. And this right here would be increasing. Okay, what's that? Oh, differentiable, which means I can take the derivative across the entire. Okay. And the continuous is the monster one. That's the big one. Differentiable one, that kind of just stabs you in the back of the one. But that's the big one. Continuous.
Me too.
All right, so as I'm doing the first derivative test simply says this. Simply says this. If I'm continuous and differentiable, right, which is okay. If I'm increasing right here and I hit some c value, right, that's some c value, and then I switch to decreasing. If I switch from increasing to decreasing, this is going to be a relative maximum. Durr, right? I like it. Okay. Right here is another c value, right? There's a couple c values, maybe called the c1 and c2. And my second c value, right? I just look on the intervals on both sides of it, okay? The intervals on both sides, and I have a decreasing section here, and then it switches to increasing. So if I'm going downhill and then it switches to uphill, obviously that's going to be a relative minimum. It's heavy.
Rocket science.
Heavy. It's crazy hard. That's called the first derivative test.
That's what we've been doing.
That's it.
Yeah, it is like what
That's all there is to it. What do you do with it? Good question. Good question. I come back to this graph right here. Let's say your graphing utility fell off the boat and you were dying to do math. Okay? And you were looking at this right here, and you have your three intervals, right? Notice that your interval gaps right here at 0 and 0, right? Notice that was a c value. That was a critical number, okay? And then 1 and 1, that was my other critical number. So on this graph, I had critical numbers at 0 and 1. So at 0 right here and at 1 right here. Now the critical numbers, that's where the relative max and relative min happen to happen. That's right. But on this one, notice that I went from an increasing section to a decreasing section. So if I'm going uphill and then I switch to going downhill, this right here, this gap right here would have been a relative maximum. Okay? Because I switched from an increasing to decreasing. Okay? Likewise, my gap, I went from this 1 to 1, 0 to 1, 1 to infinity. 1 was my critical value. So between there, I went from decreasing, so I was going downhill, and then I went back increasing to uphill. Since I switched from a negative to a positive right there, then that's going to be a relative minimum. So I've got a relative minimum at that level. Okay? Is that good? Yeah. Easy? You guys are all right?
Should go a long way. You have to find the...
Cool. All right, let's do one or two more real quick, and then we'll be done. Okay? I got to throw a couple curveballs at you.
Oh, crap.
Yeah, I'll make you do that right now.
And the calculator falling off the boat, i.e. half of the AP test, is kind of what I was trying to hint and imply. There will be half of your AP test where you won't have a calculator, and so you'll have to think about this kind of logic to figure out if it's a maximum or minimum.
So,
I think we'll be able to tell.
Well, I would hope so, but you know, you never know. You never know.
Use the law to tell us.
Okay, go ahead and let's go ahead and throw this on our calculator. What we want to do is we want to find any relative extrema, and we want to find out what zones this guy is increasing and decreasing, or constant. Could be either. Now I fixed my interval here to be 0 to 2 pi. Okay, so I've kind of enclosed this in. If it's a sine function, chances are it might have a bunch of stuff going on, right? So I want to limit it, so I don't have to do 8 bajillion intervals, you know, and then that just takes forever. Okay, so I've got 0 and 2. Those are my kind of my right and left end caps. Okay, I don't want to do anything outside of those guys. Okay, so first thing I would do is I would find critical points, and then that'll set up your domain for you. I'm sorry, that'll set up your interval for you for what you want to do. So let's first find the derivative of this guy. What'd you say it was? Oh, I thought you were right. You were?
So then why did you say it again? Just, you know.
Just being bashful.
Yeah.
Chris Hansen. Bashful.
I know, right? Weird.
I know.
That's what you'd say.
Once again, my calculator fell off the boat, so let's try this without it. Okay, now real quick, is there any spot where this is undefined? Is there anywhere where the cosine is undefined? Think about what the graph of cosine looks like. No. Right? There's no holes, there's no gaps. So the derivative is differentiable across my entire range, right? And it's also continuous. So I have both of those going for me, which is good. It's always good to check that real quick, just to make sure that this is going to work. Okay? All right, so let's go ahead and find some critical values now. Critical values have to happen in between this little range right here, 0 and 2 pi. So I'm going to set this equal to 0. No place where this is undefined. So that means I would have cosine of x would equal a positive 1/2. So I want to figure out where the cosine of x equals a positive 1/2.
Well, if you moved it, it's all one move. Double negatives.
I can do that in this class, you know. I can do that in this class. I would have had to spend a whole lesson on that in my algebra classes. Not here, you guys are rock stars. Okay, so cosine of x is the square root of 3, so 60, so pi over 3. So did you guys get x to pi over 3? I hope pi over 3, that's one of them. Now, once again, they will throw these at you without a calculator, and so you have to be able to generate your angles here, which is kind of tough. I know this is 1 and 2 because it's adjacent over hypotenuse, right? Square root of 3 would be the third side based on Pythagorean theorem, or remembering one of those triangles. And then if it's a 1, 2 square root of 3, that was a 30, 60, 90, and 1's the smallest, that makes this 30, that makes this 60. So I know that's 60, and then 60 converted is pi over 3. After I multiply 60 by pi over 1/8. Okay? Now that's one possible answer. There's actually another answer in there, right? What's another spot where cosine could equal 1/2? The bottom guy, bless you. The bottom guy right here, which would be 60 right here, which would be 5 pi over 3, exactly, 5 pi over 3. It'd be 60 here, which is negative 60, which is negative pi over 3. Negative pi over 3 is not my interval, though, so I don't want to use negative pi over 3, 0 and 2 pi. So I'd find the coterminal of that, which would be 5 pi over 3. So those are my two interval spots that I want to check. Thank you. So those are my two interval spots I want to check. Pi over 3 is the smallest one, obviously. 5 pi over 3 is the big one. Yep.
I'm still kind of stuck with finding it just manually with the triangle.
Because cosine is adjacent over hypotenuse, right?
Right.
So adjacent is 1, that's this side. Hypotenuse is 2, makes this square root of 3, right? Now, if you're doing these manually without it, you have to remember either two triangles, either a 3690 or a 454590. This one's 3690, right? It's not isosceles, so it's got to be the 3690. And then 1's the smallest side, square root of 3 is the middle side, so that's how I knew it was 60. It's got to be the middle angle, okay? And then 60, you could leave it as 60 and then, 300, right? And then just convert those to radian. Multiply by pi over
60 divided by
exactly, which is basically, yep. Okay, so those are my two spots. Now I want to set up my intervals based on these guys right here, okay? So my far left endpoint, my first interval is going to go from 0 to pi over 3. That's my first interval, okay? My second interval goes from pi over 3 to 5 pi over 3. My third interval is going to go from, do I only have 3 intervals? Yeah. Pretty sure. And then to 2 pi. Okay, so these are my intervals. I want to pick points inside of each of these. So I want to find the derivative at some point. Derivative at some point, and then derivative at some point. Once again, I'm just checking for signs, positive or negative. That's all I'm looking for. Okay? If I do positive or negative, that tells me a lot about the graph. Okay? So pick a point between 0 and pi over 3. Pi over 6, sure. Pi over 6 is a good one. Could have picked anything. But pi over 6 is a nice one. Especially if you're doing it without a calculator, right? Pi over 6. Because if it were pi over 6 is a 30-degree angle, right? And so if you had to plug it in there, pi over 6, yeah, you could do that. And then, fine, use your calculator. It's fine. Because pi over 6, multiply that by 180 over pi. 180 over 6 is 30. Yeah, it's 30. I knew just because I've done a lot of those before. And so I kind of recognize it a little bit. But anyways, that right there is going to be a 30-degree angle. You can figure that out. But we could just plug that in. So let's see what that is. Make sure I'm in the right mode. Not. See, I can screw that. So let's go 0.5, and let's go ahead and subtract the cosine of pi over 6. So pi divided by 6, and so I got a negative stuff. Once again, don't care what the number actually is. Okay. Okay, pi over 3 and 5 pi over 3. I want to pick a number between there, somewhere in that interval. Right? So what's the number between pi over 3 and pi? Good one. Pi is a good one. So 0.5 minus cosine of pi. I think. Positive. I don't need a calculator for that one. Sorry.
How do we do it?
You're right. Do cosine of pi in your head. Think about where the graph of cosine looks. Cosine looks like this. It's a 0 and 2 pi, right? So right here would be pi. So this would be at a -1. So this would equal -1. So it would be 1/2 minus a -1. So it would be 1.5 or positive. So yeah, you can do that without a calculator. I know. So thanks for confirming that. Okay, let's pick a point between 5 pi over 3 and then 2 pi. How about 7 pi over 8?
How did
I just guessed. I just made it
like
up.
5 over 6.
You could do 11 pi over 6.
5 pi over 6?
Or 11 pi.
There we go. I do 11 pi over 6.
Sorry.
Yeah, that's okay. 11 pi over 6.
Yeah, wait,
That's
Oh, yeah. That's less than 1. No, I meant
11 pi.
I meant 7 pi over 3 is what I meant. No, I meant 7 pi over 5. No.
I don't know what you meant.
I don't know what I meant. Why did I think 7 pi over 8?
6 pi over 7.
I was thinking 7 pi over 4. That's what I was thinking. 7
Yeah,
pi
I'm
over
not the one.
4. 7 pi over 4. That's what I meant. That's what I meant. Sorry. Negative anyways, right? Okay, cool.
Mr. Gumpy,
Yeah.
will it always be like opposite, like from the interval, will it always be opposite signs?
Nope.
Or what?
Nope.
Sometimes it will be like negative and then negative.
Do this
Should
one.
it go like that?
Okay, derivative of that one would be 3x squared, right? Only critical number there is 0, right? So if it went from negative infinity to 0 is one interval, and then 0 to infinity, right? If you plug in a number right here into the derivative, it may give you a positive number right here. Here's positive number. And that should make sense as far as the graph of a cubic. It looks like this, right?
Yeah.
So it's always increasing all the way through. There's a name for that. Monotonic? Monotonic.
Okay.
Anyways. All right, so no, it's not always going to be alternating. So. All right, cool. So I've got the negative to a positive, so that means I've got a negative slope, which means my graph is going down. And then it's switching to a positive slope right at the critical value, which means this is going to be a relative minimum.
We're working on this one over here.
Okay, we're going positive, right, increasing. And then we switch over to decreasing like that, so this is going to be a relative maximum. Okay, so if I switch from negative to positive, it's a minimum. Positive, negative. All right, feeling semi-okay about this?
That's fine.
Not too bad. Feel free to graph it, see what it looks like, and it'll be good. One last one, and then we're done. Okay? Last one, I promise. Then I'll stop talking. I felt like I've talked a lot today. I have. But it's funny, this is only the third problem that we've done. Right? Isn't this only the third problem?
I do recycling needs for 2 showers.
So we're on the hunt for those critical values. Set up our intervals. And then we'll see where it goes. Go for it. Try. You do the derivative, at least. I'll do it too. Worries. I'm done. That could be wrong. There's a lot of ways.
That's right. That's right.
Wow.
Wait.
You factor on an X?
Yeah.
Oh. Why? Oh. Where and why?
I love that movie.
Quotient rule. Squared the denominator, brought it up here. Derivative of the numerator was 4x cubed. Minus, I should put parentheses here. Sorry. I did it in my brain. The parentheses. And then I did the derivative of the denominator, which was x squared, so 2x. So I multiplied 2x by the numerator. 2x times x squared plus 1 gave me this. And then a little bit of like terms got me here. And then I factored in an x out of all those in here. I did a quotient rule.
So after that, then would you distribute x squared times 4x cubed?
Yeah, wouldn't that just make it 4x to the fifth? Be like terms.
Yeah. Yeah, 4x to the fifth here, right? Minus 2x to the fifth. So that gave me 2x to the fifth.
How'd you get that last step?
Oh, it is 5.
Here to here?
Yeah.
Factor an x out of all. Or cancel an x out of all of them. And factor the 2 out. Right. Okay. So let's go ahead and take a look. We've got to find our critical numbers, right? Critical numbers are where it equals 0 and where it actually equals undefined. So I want to set the bottom equal to 0 as well. So top equals 0 and bottom equals 0. I think the top equals 0. What's that? Plus or minus 1, maybe? So my critical numbers right here are going to equal plus or minus 1. And then 0 is my other critical number. Because that's 0 would make the denominator 0, a.k.a. undefined. Critical.
Wait, so a critical number can be undefined?
A critical number can be undefined. Yep. Critical number can be
What's the thing
undefined.
that can't be undefined?
Let's see. You can't use Rolle's theorem for undefined if it has a sharp corner. Can't do that. What's the I? Oh, it's plus one. Okay. Sorry. My bad. Okay, so my intervals here, negative infinity to negative 1 would be my first interval. Then I go negative 1 to 0, I believe. 0 to 1, and then 1 to infinity. So I think I have 4 interval points to check. Yeah.
Wait, how'd you go from 2x to the fifth to minus 2x to 2x4?
On this part right here, because I factored an x out of all of those. And then that cancels with one of them on the denominator. Okay, once again, I'm just checking for positive or negative is all I'm really looking for here. Okay. Okay, so these are going to be my zones for which we're increasing and decreasing, hopefully. So pick a number in this little interval, and just to make life a little better, nothing wrong with graphing your derivative, just so you have a thing to plug in values on, right? It's a little cheating, but you could do it by hand if you were forced to, but, just to save you a little bit of time. So let's see, so it'll be a 2x to the 4th, and then minus 2, and then divide, whoa, I feel like that's going to get screwed up. Divided by x,
You don't want to get what?
oh, I was supposed to put it in there.
If you put it
There
on
you
the
go.
equal
You put it on
sign.
the equal sign.
That's a good spot to put it, just in case.
Alright.
What happens when you like do that equal sign? What does that do?
I don't know.
You like highlight it?
To be honest with you, I'm not sure.
I feel like when you highlight the equal sign, it means that something comes to that.
Okay, so let's find some points. So I'm going to go -2. Sure. Hey, it's negative. I'm going to go negative 0.5. Hey, positive. I'm going to go 0.5. Hey, it's negative. I'm going to go 2. Hey, it's positive. Cool. Okay, so I switched from a -2 to positive, so downhill to uphill. So this is going to be a relative minimum. And I'm going from a -2 to positive, so another relative minimum. Bad. Why is it bad? It's a good question. Think about why it's bad while I type it in here real quick.
Bad.
Zero was the spot where it was undefined, right? Right? What are the stipulations on this relative min, relative max, increasing, decreasing, first derivative test? Continuous and differentiable. Okay, it's got to be continuous and differentiable. The original function is not continuous. Okay, it's not. It has an asymptote at 0, right, from the original equation. Can't see that. Asymptote at 0, right? So it's not continuous. First off, and it's not differentiable at that point either, because where it's this is a critical value right here, but that's not defining the derivative. Not you're not getting a number for the derivative there. Okay, you're getting where it's undefined. So backfires on you. Anyways, so that one bad doesn't exist. Okay, there's no anything right there. Okay.
Why does that happen?
2 reasons. One is not continuous, right? And the second one is it's not differentiable at 0 rate.
I mean, if you looked at the initial graph, I mean, it doesn't hit 0.
True. But what's the derivative at this point right here at 0? It's undefined, not a specific number, right? So since I don't have a specific number right there, it's not going to be. It's not good. No relative max or relative. So, say it again.
So it's all kind of like
They're kind of like a couple travelers swinging down there. Yep, that's what they're like. So we're on 186, and we do 345.
So in that last question, what would be the answer?